Okay, hello grade 12s and 11s. So today we'll be tackling a question on Newton's laws, and it's fine even if you don't know and you don't understand Newton's. This would definitely be a good opportunity to know that. I'll go through basics of Newton's while attempting this question. I'll try to tackle the basics of Newton's, so to bring everyone up to speed. So if you're still left behind, don't worry, you'll catch up very quick. Okay. So Newton's laws, we have Newton's first law, Newton's second law, Newton's third law. And Newton's first law is usually also known as the law of inertia. Basically, where they use a seatbelt, where it says um, a body will remain in a state of rest or uniform motion unless acted on by a balance force. The example they will use an example of a seatbelt that if you are moving in a car and a car is moving at 80 kilometers, you are also moving at 80 kilometers. And if let's say the car brakes, you will keep on moving forward with the same speed, but because of the seatbelt will stop you. But basically that's Newton's first law. Newton's second law, when you apply force on an object, the object accelerates in that direction, and the acceleration itself is directly proportional to the force and inversely proportional to the mass. If you think about it, you take a chair, you pull a chair or you push a chair in a certain direction, that chair will go in that direction. And if you start applying more force, it will accelerate in that way. If you start, maybe if let's say you were walking and then now you start running while pushing the chair will accelerate in that direction that you're pushing it. Now, but if the same chair, but now we add more stuff, let's say now on top of that chair we start adding books, we start adding bricks on top of that chair will become more heavier to pull, and that means your acceleration will be less than what it was when the chair had nothing. So basically that's Newton's second law. When it says the acceleration is directly proportional to the force and inversely proportional to the mass, while when the mass increases, acceleration decreases. Basically that's the thing. So when I want to increase acceleration, I increase the force. But when I want to when I want to decrease it, I increase the mass. Then he gave Newton's third law that when an object is applied on another object, or when object A pushes object B will push back with the same magnitude but in the different direction. An example would be a person pushing a wall. When you push a wall, you push a wall with a certain force, and the wall exerts uh, the force of equal magnitude to you but in a different direction. Okay, now here we have a block of mass 4,1 kg connected to block B of mass 2,3 kg by a light inextensible string passing over a frictionless pulley. Block A is at rest on a rough horizontal surface and block B hangs vertically as shown in the diagram below. A force F of magnitude 49 is applied on a block at an angle of 50 degrees to the horizontal, causing block A to accelerate to the left from rest along the table. The coefficient of kinetic friction between the table and block of A is 0.35. Now, in Newton's, there are wordings or there are words that you have to pay attention to. For example, light inextensible string, when they say light inextensible string, that indicates tension. They usually indicate tension. When they say rough horizontal surface, they're indicating to you that the surface, there's going to be a frictional force. So once they say smooth surface does not have friction. We do not have friction on a smooth surface. But once they say a rough horizontal surface or a rough surface, we have friction. And it's the same. They use the same concept in work energy. When you work energy, when you say rough, there's friction on that. So yeah. Now, just to cover the basics. Basics Newton's first law. For example, if you have a block on a rough surface, let's say this is a rough surface, and you have a 5 kg block, you will have forces acting on that block. Let's say in this case the block is standing and it's not moving. In this case, you will have your normal force acting upwards, because the definition for normal force is a force that the object applies on an object and is always perpendicular to the surface. So that means your normal force is perpendicular to the surface. Perpendicular, if you think of perpendicular, you remember to maths, perpendicular 90 degrees. If you think of perpendicular 90 degrees. Now, That's what it means. Because if you look, it's always perpendicular to the surface. If you think of this normal force, if I extend it to the surface, you see it will form 90 degrees with the surface. Now, that's normal force. So normal force going up and your gravity going down. Now, when it comes to gravity, it's easy because gravity is always acting down. Whether you are on a flat surface, on an incline, even in the air, gravity is always going down. I mean, even if you have an incline like this and you have a block, your gravity will always be downwards. Same direction, downwards always. Gravity is consistent. It doesn't change like that. It's downwards. So yeah, so in this case, I will say our normal force is equals to Fg. And sometimes when you are asked to calculate, in grade 11 they'll ask you to calculate normal force will be Fg in this case. Normal force will be Fg, which means Fg will mg. So this will be your mass, and this will be your gravitational acceleration. So mass is in kg, and this is meters per second squared. So this is your constant, your 9,8. And this will be the mass of the object. So that will be, in this case, will be 5 multiplied by 9,8. That will give me the normal force for this object. Now, same scenario, but now I'm adding the rough surface, or let's say the object is moving now. And I'm adding a force applied to the right. And now that means if I add force applied to the right, that means there will be a frictional force. Because frictional force is a force that opposes the motion of an object and is always parallel to the surface. By parallel, if you remember parallel are two lines like this, in the same direction, but they do not touch each other. So if it's parallel to the surface, that means even the surface is on an incline. If your surface is on an incline, your friction will be parallel. This will be FK, parallel. Even if your surface is like this, your friction will still be parallel. That's what parallel means. So your friction is always parallel to the surface. So remember that. Now, with your friction is the force that opposes the motion of an object. So if you're pushing your object to the right, friction to the left, it will go to the left. If you're pushing your object to the left, friction will go to the right. So that's friction. It opposes the motion. Now, if let's say you have an object like this, and now we have force applied in friction. Still in this case, your normal force will still be equals to your Fg, because now you look at your horizontal and vertical forces. Your vertical forces, I only have normal force and my gravity, which means my normal force will still equal to my gravity, which will still equal to Fg. And my if I'm now concentrating on the horizontal forces, I will have force applied in friction. So I will minus force applied from friction to get magnitude of the forces in the horizontal. But now, if your force applied, remember this, if your force applied is now being applied at an angle, if it's not applied horizontally but it's now being applied at an angle, like in this scenario that we're going to look at, if it's being applied at an angle, just know that in that case your normal force is not equal to Fg. So your normal force is not equal to Fg, and we'll explain that in a second. So in this case, your normal force is equal to Fg minus Fy. So this is subtraction. So minus Fy. Now, you still remember in grade 11, we started in term 1, you did your so for mitigation, this is a revision. In grade 11 term 1, you did vectors, sorting out vectors. When you had a vector, when you're sorting out vectors, you would resolve your vectors in terms of your vertical component and your horizontal component. So in case, let's say I have 5 Newton, I will resolve it into my vertical and horizontal component so that I can solve it, so that I can subtract or add it. Because when it's like this as a vector, it becomes hard for me to add it. Because if you think about it, let's say I have 7 Newtons and 5 Newtons acting in that way. If I don't resolve them in terms of their x and y component, it will be difficult for me to add them, because I can't just say 7 plus 5. Because after I add them, what will be the direction of my vector? Because the other one is going that direction, the other one is going that direction. What will be the direction? Will the direction be up? Will it be going this way? What will I choose? So it becomes hard to know. But if I resolve it in terms of my x and y component, it becomes easier, because now I will have the horizontal forces and the vertical forces. Now look at this. Now if I resolve this, then I can see that the horizontal forces are going in different directions, so I can subtract them. Their vertical forces are going in the same direction, so I can add them. So it's easy. So that's the whole point of vectors, so that I can resolve it. So then come back here. So in this case, because force applied is applied at an angle, that means I'll have to resolve it into its x and y component. And if I resolve it into its x and y component, look at this. Let's look at our horizontal forces. The horizontal force that I will have is what? Fx going in that direction and Fk opposing the motion. That is, so Fk, that will be my kinetic friction. So that will be Fk opposing the motion. That's horizontal. But we look at the vertical now. The vertical forces, we have normal force going up, but we also have what? Fy. Fy, that is what? The vertical component of the force applied. So you see now, not only normal force that's going up, but it's also Fy. So that means normal force plus Fy will have to equal to Fg. Normal force and Fy are the ones that are balancing Fg. So Fg is now normal force plus Fy is Fg. So if I want to calculate normal force in this case, normal force will have to be Fg minus Fy, because if I take Fy is positive, if I take it to the other side it's negative. So then it's positive this side. If I take it to the other side, it becomes negative. So that is why I get normal force is equals to Fg minus Fy. So if I wanna, that means if I wanna calculate, so that means if I wanna calculate my normal force when this is applied at an angle, when my force applied is applied at an angle on a flat surface, then my normal force is Fg minus Fy. Because of this, because why? Because two forces are going up, Fg is going down. So normal force plus Fy is equals to Fg. It's no longer just normal force is equals to Fg. And your Fg obviously is still your Fg is still your mg, and your Fy that is your, that will obviously be your y component. So that will be Fy, which Fy, that is f minus f sine of theta. Okay, now we'll do another time an example of on an incline, but just to cover that out as well, on an incline is still the same. For example, on an incline, if we go to an incline, our normal force we said is perpendicular to the surface, right? So when on an incline, even on an incline, your normal force still remains perpendicular to the surface. Does not change just because now we are no longer on a flat surface, we are on an incline. That does not change. Your normal force still remains perpendicular. So that means if I have an inclined plane like this one, my normal force will still be perpendicular because it still needs to form what? 90 degrees with the surface. So just like this one, it still needs to form 90 degrees with the surface if it is on an incline like this. Even if it's like this, my normal force still needs to form a 90 degrees, so it will go in this direction. So it does not change. So in this case, my normal force, if we do had an incline like this, my Fg is consistent. As you can see, it's going down, but my normal force will go up. Here's my normal force going up. Is my normal force going up. Now I will have, let's say I had force applied, Fg will still be going down. But when you get to an incline, you'll see when you do, we'll cover this a lot when you do another example on an incline. But in an incline, we have Fg parallel and Fg perpendicular, and those are the components of gravity. But this only occurs when you're on an incline. On a flat surface, we just have Fg. We deal with that. So we'll deal that more when we get but basically Fg perpendicular is your mg, because Fg, remember, is what? Mg, mass times gravity. So this one will be your Fg perpendicular is your mass times gravity cos theta, and your Fg parallel is mg sine theta. But you will discuss the how, and you will also see that when you do an incline, that your Fg parallel is always down the incline. You will see whether you have an incline going in this direction or heading or an incline in this direction, these two directions, you will see that your Fg parallel is down the incline. But we'll do that more when we cover the incline. So let's come back to this one. Now, if you have a flat surface, now we say Fk, that's your gravity, as we've mentioned, that's your frictional force. Now we have two kinds of frictional force, kinetic and static. Kinetic occurs when your object is moving. So when there's movement, that's kinetic. When it's standing still, that's static friction. So if it's a rough horizontal surface and it's standing still, that does not mean there's no friction. There is friction, but now it's a static frictional force, not kinetic. It becomes kinetic when the object is moving. but it's still the same. To calculate it, UK multiply by normal force. If it's static, US multiply by, and this UK or US, basically this is the coefficient of your kinetic friction or coefficient of static. And to identify a coefficient, they tell you on your statement that is a coefficient, but it does not have value. It doesn't not have units. So when it's usually 0 comma something or 0, it's 0 comma something, and it does not have units, you'll never see it 0 comma 12 newtons. It does not have units. You'll never see it with newtons. You'll never see it with meters per second or meters or anything. It's 0 comma something. It's just as that as a number. It does not have units. That's a coefficient. Okay. So now let's get into the question. So we've told that the coefficient is 0.35, and as usual, the first question I'm sure it will be the definition. So we have two, as you can see, we have two blocks, block A and block B, 4,1 kg block A, 2,3 kg block B. State Newton's second law of motion in words. That's 2 marks. So it's important that you study your definition so that you can definitely get that mark. Draw a labeled free body diagram showing all the forces acting on block A when it accelerates to the left. So block A, that's the 4,1 kg. So we'll do for both. We'll draw for both blocks. But now you see that there's a mark allocation. So the mark allocation next to the free body diagram indicates how many forces you're gonna have on your free body diagram. So for example, on this one, because it's a free body, it's a dot. So if it's a free body diagram, you use a dot. If it's a body diagram, you use a block. Free body, dot, body, block. Okay. So in this case, because we have force applied, it's being applied at an angle, so that you must show. So it must not be this, it must not be like this. Your force applied must not be like this. When you can see on your diagram, it's at an angle. If it's at an angle, it must not be like this. This is totally wrong. You get it wrong if you do that. Because it's at an angle there, then even on your free body diagram, it must show that it's at an angle. You don't have to measure the angle here, but it must show that it's at an angle, so it must not be straight. And your normal force going up, your FG coming down, then you have an inextensible string, which is your tension. So your tension will be to the, on the 4,1 kg, your tension will be to the right, but on your 2,3 kg will be up. Why? Because by the 4,1 kg is tied to the 3 kg block, so it's pulling the 2,3 kg block, and the 2,3 kg block is being pulled. So it's also being pulled, but it's almost like it's also resisting to be pulled. So that is why you will see when you do for the 2,3 kg block. But for the 4,1 kg, if I'm doing a free body diagram, that's your force applied, Fg, and Fk. Fk, that is your kinetic friction, because we know we are told that it's moving to the left. So tension and Fk go in the same direction. So you see I have 5 forces: normal, gravitational force, force applied, tension, and F of K. Another way I can do it like this. This will give me six forces, but it's basically still 5 forces. Why? Because instead of writing force applied like this as force applied, okay, I can write it as, you can write it as it's in terms of its components. So that will be f of x and f of y. But to avoid getting it wrong, because sometimes to avoid having a vector like this, having a vector that in this direction on your Cartesian in this direction, and you writing and maybe taking the f of x to be this direction, but then taking f of y to be this direction and confusing it. To avoid that, just make sure that you just write the force applied and leave it as that. So write it as the force applied like that and leave it as that. Okay. So for the 2,3 kg block, there was only 2. If there was a question for the free body diagram, it would only be 2 marks. Why? Because we only have a gravity pulling down. Remember, we said gravity is always there. Whether something is hanging in the air on a flat surface, doesn't matter where. Gravity is there. So now, gravity is pulling down. tension pulling it up, because remember it's being pulled up. Because remember, as I said, the 2,3 kg block is being pulled up by the 4,1 kg block, and the 2,3 kg block is also trying to pull the 4,1 kg block down, but it's not enough. That is why if you look at the 4,1 kg free body diagram, we are taking its tension, we're saying tension to the right, because the 2,3 kg block is trying to pull it to the right. But when you come to the 2,3 kg block, 2,3 kg block is trying to pull what? The 4,1 kg. But it's being pulled up. So the 2,3 kg is trying to pull the 4,1 kg down. So but it's being pulled up. So the tension for the 2,3 kg will be up because it's being pulled up. But the 4,1 kg is being pulled what? To the right by the 2,3 kg. Yes, it's not going to the right because there's a force being applied to pull everything to the left. But in terms of the tension between the 4,1 kg and the 2,3 kg block, we're writing this direction because basically the 2,3 kg block is pulling the 4,1 kg. So that will be tension in Fg. So as we said, in this direction, because as we said, so if I have to calculate my frictional force, because my force applied is being applied at an angle, my normal force is not going to be equal to Fg. Instead, it's going to be equals to Fg minus Fy. Explain that. So then, I think that was the first question. So the first question they said calculate the kinetic frictional force exerted on block A. So that will be Fk, Ukn, and N is Fg minus Fy. And Fg minus Fy, our Uk or coefficient is 0.35 multiplied by 4,1 multiplied by 9,8. 4,1, that is your mass. Because remember, if you do it like this, it's going to be Uk, and then your Fg, that is your mg, minus F of y, that is force applied, sine of theta, force applied sine of theta. So that will be 4,1 multiplied by 9,8, subtract force applied, which is 49, sine of 50 degrees, which is the answer is 0, I'm going to put it to 3 decimal place, 0.925, or you can say 0.93 newtons. Question usually specifies how many, whether to do it to 2 decimal place or more. So calculate the acceleration of block A by applying Newton's second law to each. So when I'm doing that, so let's go back to the diagram. So when I calculate the, oh, this is not showing, sorry. So basically this will be for the, this will be my basically my FK. My FK will be UK times N, Fg minus Fy. Then this is why I substitute my UK. My Fg will be mg, my Fy will be Fa sine theta. Then all I have to do is substitute. 0.35 multiplied 4,1 times 9,8 minus 49 sine of 50 degrees. That will be 0.925 newtons. Now, I come to, now they told me to calculate the acceleration. So now, and they told me to use basically the both blocks. Now, if I start with block A and block B, we look at there, because the free body, it's important to get the free body diagram right, because the free body diagram guides you in terms of what forces to use. So I'll choose that I'm going the horizontal forces for block A. So F net is equals to MA. So I know I have the force being applied at an angle, so I need to resolve it to its x component, which is f of x. So for the block A, it will be f of x minus tension minus f of k, which is my kinetic friction, because if my tension and kinetic friction are going in the same direction, they are opposing f of x. So that will be negative if I make f of x positive. If I make f of x negative, I will have to make my tension and kinetic friction positive. Is equals to ma. Then f of x is f cos theta minus tension minus f of k. I've already calculated my kinetic friction, which is 0.925, and then f, this one 49 cos of 50, and then minus tension. I don't know what my tension is. I go to the second block. Block B, f net is equals to ma. T minus f of g is equals to ma, because that's the only two forces acting on the block. So tension minus gravity. Now 2,3 minus 9,8. Then I get T. Minus 22,54 is equals to 2,3a. On the other side, I get 49 cos of 50 degrees minus 0,925 is equals to 30,572 minus tension, which is equals to 4,1a. Then this will be my equation 1, and this will be my equation, and this will be my equation 2. This will be my equation 1. Now, once I hear, it's most like I'm going to equate, but I'm going to do it with a shorter version. So, but to do this, I have to make sure. So on your just another thing on equation, just make sure that you have the right signs. Check your tensions. Make your tension on block A and your block B can't have the same sign. So for example, on block A, my tension is negative. On block B, my tension can be negative as well. Why? Because if you look at my free body diagrams, my tensions are going in different directions, right? In a way, why? Because the other one is coming this way, the other one is coming this way. But if that is why my tension this side is positive, the other side is negative. And it's also going to help me when I equate. So it's going to also help me when I equate. So in this case, because 30,572 minus tension is equals to 4a, so what I can do here from here to shorten it, because the other one is negative, the other one is positive, I cancel them straight. Then I do what? 30,572, this is negative 22,4. Then I subtract them. Then 30,572 minus 22,4. So I cancel the tensions, subtract the numbers, then add the accelerations. I subtract the numbers and I add the accelerations. So 30,572 minus 22,54 is going to give me 8,032. 4,1 plus 2,3 is going to give me 6,4a, still acceleration. So divide by 6,4 divided by 6,4, my acceleration is going to give me 1,26 meters per second squared. And that's shortened method, easy as that. I make sure that when I get here, so when you get here, you keep your acceleration on that side, you don't bring it this side, you don't give it like that, and you keep acceleration on one side and everything else on the other side. Then you make sure that your tensions have different signs, then you cancel them, then you subtract the numbers, add the accelerations, then you get this simple method. And after you get your acceleration, it's easy. Sometimes when they will ask for tension instead of acceleration, and usually you get your acceleration. After getting your acceleration, you will just have to substitute in one of these equations. If you substitute acceleration in any of these equations, you will get the same tension. And basically, that's it. Simple as that. That's newtons. And really, that's all compiled. So yeah, then we'll do more example in the future on incline plane. Just before you write, we'll do one on incline. And yeah.